as he said, I'm David Lingenbrink. I'm a student at Cornell. My advisor is Krishnamurthy, Iyer. And I'm going to be talking about optimal signaling mechanisms in unobservable queues with strategic customers. We're going to start with a very highly stylized example, Uber. So imagine you land in Boston Airport and you don't want to wait too long to get a ride from the airport, so you're trying to decide between Uber and a taxi. There are advantages to both. Taxis rides are going to cost a lot more, but they're readily available. Uber costs less, but you're going to have to wait in a queue of other travelers till a driver is available. You're going to make your decision of which to use after Uber gives you an estimate of your wait time. The question I have is, what information can Uber provide to you to encourage you to use their service? There are some quick ideas that I thought of stuff Uber could tell you. First, they could fully reveal their estimate of how long it's going to take till you get a ride. That'll be helpful to you, but a disadvantage to them is that customers won't join when that wait's long. They could give you no information, and then all customers will have a fixed probability of joining the system, but you're going to miss customers when there's 0 minutes of wait who otherwise might use your service. Or maybe you could give some partial information in between these two to encourage customers to use your service. These types of questions show up in a lot of other settings. Call centers could be telling you, how long it's going to take till you talk to a representative. I've definitely had experience with that. At amusement parks, they give you an estimate of how long it takes to ride the ride until you get to the front of the line, but they might obfuscate that estimate in order to encourage you to actually visit that ride. So our general question is how a service provider can disclose information to customers to encourage their participation in a queue and thereby increasing their revenue. This is an instance of Bayesian persuasion in a dynamic setting. Bayesian persuasion was introduced by Ryo and Segal, as well as Kamenika and Genskow, and has generated a lot of subsequent work. Mansour looked at incentivizing exploration in multi-arm bandit problems. Bergman and Morris found connections between Bayesian persuasion and Bayes' correlated equilibria. And Dugmi and Zhu took an algorithmic approach to finding optimal signals when there are no externalities. But we're more in a dynamic setting, which is different than these models, where these signals are provided sequentially to arriving customers. And that actually changes things a good amount, as we'll see. So we're going to go over the model, and then we're going to go over the equilibria that this model produces, and then we have a couple of problems we're going to tackle. So for the model, we have a MM1 queue. Customers are going to arrive according to a Poisson process with rate lambda. The queue is unobservable to customers, who must all make their decision when they arrive of if they're going to get in the queue or not. Joining customers are going to pay a fixed price P and then wait in a first in, first out queue to attain service. And finally, service time is exponentially distributed with mean 1. Customers are homogeneous and delay sensitive. Customers who don't join the queue receive utility 0, but those who do receive utility given by that function, where V, which we're going to set to be 1, is the utility the customer gets from the service. P is that fixed price, so 1 minus P makes sense for the utility. And then G of X is the expected waiting cost function, given there are X customers in front of you in the queue. We're going to put some assumptions on G. We assume that customers don't enjoy waiting, so that G function should be non-negative and also non-decreasing, like that G I drew up there. They would join an empty queue, so it should be the case that customers want to join when there are no customers. And then customers would not join long queue. So eventually there's a point where the queue is so long that customers no longer wish to join it. Now, we've talked about the customers. We're now going to describe the service provider. The service provider aims to maximize their expected revenue by their choice of a fixed price P, as well as a signaling mechanism. Now, a signaling mechanism is both a set of possible signals as well as a mapping from lengths of the queue to distributions over those signals. So in other words, we might define the signal sigma, where we put in sigma ns, where that is the probability of sending signal s given that there are n customers in the queue. So some quick examples. The no information signal, maybe the set of signals is just the empty set, and we're going to send the empty set with probability 1 for all queue lengths. You could give full information, then the set of signals are just the non-negative integers, and then we're going to send exactly how long the queue is to every customer. And finally, one last example. Maybe your set of signals is the possible queue lengths, the non-negative integers, as well as the empty set, and you're going to either reveal the full queue length or give them no information, each with probability of half. So we've now explained the model we'll be operating under, but this model also induces an idea of an equilibrium, which I'm going to describe. So a customer strategy, a response to what the service provider is doing, is a function f such that given a signal s, a customer joins with probability f of s. So that's how we're going to indicate the strategy of a customer. Qn is going to be the probability that a customer joins given there are n customers. So in other words, Qn is, no matter what signal it sends out, what is the overall probability that once a customer arrives and there are n customers, that they do ultimately join the queue. Now using this Qn, we can actually write this whole problem as a Markov chain, where the states are the number of customers in the queue, and then our rates are based off of rate 1 transition going from state n to state n minus 1 for the rate at which customers are leaving the system when they're being served, and the rate going upward is lambda, their arrival rate, times the probability of once they arrive, them actually staying in the queue. So yeah, it's a Markov chain. We're going to let pi denote the steady state distribution for this Markov chain, and x infinity to be a random variable drawn from pi. Now, we've given the idea of a customer strategy. A customer equilibria is going to be, a symmetric equilibria, is going to be a strategy that maximizes a customer's expected utility under steady state, assuming all other customers follow that. In simpler words, this means that it is a strategy where customers are going to be joining the queue when the expected utility is better than not, and not joining when it's better to not. It's basically assuming that customers are going to be behaving in their best interest. So now we've defined this equilibria, we can define the service provider's goal, which is to maximize their revenue. And the revenue is going to be given by price times the rate at which customers are going through the system, which is the rate of service 1 times the amount of time when customers are there to be served, which is given by 1 minus pi naught, the rate at which there's anyone there to be served, which we can also express as just p times that sum of basically every state except for pi 0. Now this leads us to define our two main problems for this talk. One, given a fixed price p, how can a service provider choose a signaling policy to maximize their expected revenue? And two, how can a service provider choose a price p and a signaling policy to maximize their expected revenue? So the only difference is in the second problem, you can choose the price, where in the first one, it's selected for you in advance. So let's start on that first problem. But to do that, I want to note that unlike other settings of dynamic or of Bayesian persuasion, our situation is dynamic. So the signal you receive, yes, affects a customer's posterior. Once they receive a signal, they have a better idea of what the current length of the queue is. But it also affects their prior, because the choice of a signaling mechanism affects what customers think about the decisions that other customers are making. So it can affect, even before you receive a signal, the signaling mechanism actually affects your prior distribution. So we're going to start with handling the case where there's a fixed price. First, a quick lemma. It suffices to consider signaling mechanisms where the set of signals are just 0 and 1, not join and join, and the customer equilibria is obedient. The customer just follows your recommendation. And this is proven using a standard revelation principle style argument. Next, our first major theorem is that for any price and any weighting cost function satisfying those basic assumptions I mentioned earlier, there exists an optimal signaling mechanism with a threshold structure. A threshold structure is of this form. What that's saying is that you're going to tell customers to join up until a certain length. At one length, you might randomly tell them to join or not join. And then afterwards, you're going to always tell them to not join. So very much as a threshold where you're going to tell them join, 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 and then not join. The way we prove this is first, here is our decision problem. We're trying to find the signaling mechanism that maximizes the expected revenue. Given that customers, when given the signal 1, should want to join, that expectation should be greater than or equal to 0. Customers who don't want to join or are told not to join should not want to join. So that is the thing we'd like to maximize. But first, we can write those expectations in terms of pi, the stationary distribution. So we can rewrite this as that. I'm still maximizing over sigma, but using the stationary distribution that falls out of it. But then we realized we could actually just, instead of maximizing over the signaling mechanism, we can maximize over the stationary distribution itself. So we can just rewrite this with a pi there under the max. And this is actually a linear program, which makes our analysis quite a bit easier. And now that that's a linear program, the remainder of the proof consists of perturbing any solution in this linear program to a threshold mechanism without decreasing the utility. And that's how we prove this result. And we've proven this analytically, but to show it numerically, here are some plots of the revenue of the full information, no information, and this threshold mechanism. The revenues of them for both, first, different lambdas. This is different arrival rates. As we'd expect, threshold is outperforming both, as well as this is decreasing. As you move along this line, you're decreasing customer patience. But either way, threshold is outperforming as we'd like. So we're now going to talk about our second of two problems, which is where you're allowed to choose the price. It's still going to be a fixed price, but the signaling mechanism can choose that price to maximize revenue. So exactly what I just said. But we're going to compare this against a very well-studied area, which is where the prices are state-dependent in a fully observable queue. This was originally studied by Noir, but has been expanded upon. So here the service provider sets prices Pn for each state. So customer arrives and is told what the price will be for them to join the queue. And they're going to choose a cutoff K such that at that point they're going to say the price is infinity and customers will never join. As well as they're going to choose prices to extract the entire customer surplus. So actually your P of n is going to be 1 minus G of n, basically ensuring that customers who join will receive zero utility but will still join. So this is another model. Again, this is in the fully observable model. But the big question is, how does our revenue, the optimal revenue under our signaling mechanisms, compare with that of the optimal state-dependent pricing mechanism? And it's unclear to me just because each has benefits over the other. And our second big result is that the revenue is actually equal for the optimal situation. You get the same optimal revenue from both. And the way you prove this is first, and I'll show you one direction, under the optimal state-dependent prices, the expected revenue is going to be that expression. We have just the indicator of, if a customer arrives, is there room for them? And then this is actually just that P of n, it's 1 minus G of n. We now construct a threshold mechanism where the price is the expectation of the price from up here. Here I have plotted both the state-dependent price for a specific set of values, and then what the fixed value would be. Basically, you're able to construct a fixed, a signaling mechanism with a fixed price that attains the same revenue. And you can do the same in the other direction. What's interesting to me about this is that in settings where it is infeasible to charge state-dependent prices, you can actually extract all that revenue just by obfuscating the information available to the customers. So this optimal signaling can actually get that same revenue, even in settings where changing the prices doesn't make sense. So now we will conclude. So we study dynamic Bayesian persuasion in a queuing setting. We have two major results. The optimal signaling mechanism under a fixed price has a threshold structure. And under that optimal fixed price, optimal signaling achieves the same optimal revenue as state-dependent prices. Some extensions we're looking into. One is heterogeneous customers, if there are two types of customers. It actually complicates the optimal signaling a fair amount. As well as imagining restrictions on the signals. For example, if customers already had some idea about the information, what signaling could you do to maximize revenue? But thank you.